Welcome, my dear students and learners and my friends. Especially my sincere thanks to Pankaj to give the opportunity to share my knowledge and discuss about this topic. So even though it was delayed, I was slightly busy at site. So I have framed the content of the discussions. This I have made considering the courses, my courses in training school also. So today just I am going to discuss about the topic which I will elaborate in some 10 or 15 lectures. So the topic name I have given as Introduction to Fast Reactors. So here we are going to discuss each topic will be discussed in one lecture. So the first lecture will be on necessity of fast breeder reactor and 3-stage India nuclear program. Even though all we are from nuclear field, they will be knowing most of the things, but still I am starting it from the scratch and with the basics, so that it will be also useful for the students. So whenever we are going to do something, we are as a professionals or as a student, whenever we are going to do anything, we should know why it's needed, why we are going for FBR, why we need breeder reactors, and what is the 3-stage India nuclear program, why it is thought that 3-stage nuclear program, why it is required, and how we will be benefited. So in the first lecture we will be discussing that. Then we will understand the basics of reactor physics, nuclear fission, because the main concept behind the nuclear reactor is the nuclear fission, and the concept of breeding. Breeding means it is reproducing, something reproducing. So that we will know. So far in the country, in India, the reactors which are operating and contributing the nuclear energy to the country are the pressurized heavy water reactor. So we'll know some comparison of fast reactor and pressurized heavy water reactor. It's a deuterium oxide. Heavy water means deuterium oxide reactor. Then needs and advantages of sodium cooled fast reactor. So the India's 2nd-stage nuclear program, the coolant is sodium. This will be used for heat transportation, and this coolant will play the major role to convert the thermal energy to mechanical energy, as it will transport the heat from inside the reactor to expander, to turbine. Okay. Then the design uniqueness of fast breeder reactor for the efficient use of natural uranium, depleted uranium, and plutonium. So this depleted uranium, mainly for depleted uranium and plutonium, is to be used efficiently for breeding, because that is the byproduct from heavy water reactor. Then we will be knowing the comparison of various fast reactor like কি কোড দিয়ে ভরে দিয়েছে ছেলেপেলেগুলো, এবারে বুঝতেও পারছি না এগুলো কি। Next will be the comparison of various fast reactor like sodium cooled fast reactors, lead cooled fast reactors, then molten salt reactor and gas cooled reactors. Next we will discuss about various fuels in fast reactors like oxide fuel, metallic fuel, carbide fuel, and selection of fuel in a fast breeder reactor in India. Then we will be knowing mostly about the systems and some major components in PFBR. Here I will discuss elaborately few special components like electromagnetic pump, where it's a very interesting hydraulic device where the Navier-Stokes equation, momentum equation and Maxwell equation contributed cumulatively to produce the head and discharge. Electromagnetic flow meter for liquid metal sodium flow measurement. And what are the techniques and methods, advantage, disadvantages, how to overcome it, all these things we will discuss. Then in comparison to pressurized heavy water reactor, all the coolant circulation system, the prime movers are direct online structure. But here we have used a variable frequency drive to operate the prime mover of primary and secondary coolant system. So we will know about slight in details about the variable frequency drive system used in PFBR. Then the pony motor and its role in primary coolant system. Pony motor, it's a geared motor, small motor, and how it is coupled with the main motor using some mechanical overrun clutch. It's a centrifugal overrun clutch. So it will, even though we know the primary coolant motor will be powered through class 4 system, it will fail anytime. Even though it's failed, but the RPM will not, it will suddenly, the coolant pump will not stop. This pony motor will take care to operate it, to rotate it. With the pony motor is supplied, this power is, the pony motor is fed through a UPS of backup maybe 3 to 4 hours. So we will know about the pony motor, how it is connected, what is mechanical overrun clutch, and how the engaging and de-engaging. It's a, as I told you, it's a centrifugal overrun clutch. I have seen its manufacturing. It's imported from foreign, I think Stuttgart or somewhere. So how it is manufactured, and it is exactly when due to centrifugal force the cam is getting actuated exactly at the designed RPM, and it is also engaging. It's very interesting. I was very eager to see that how it's happening, because electromagnetic based overrun clutch I have seen, but this such extensive application of mechanics, solid mechanics is used here. So we will know in details. Then the large electrical machines in PFBR, like boiler feed pump motor, our CO system motor, primary and secondary coolant motor, condensate extraction pump motor, all these things and mainly the step up transformer for the substation. It is around, our power is 500 megawatt with some power factor maybe 0.8 or 0.85. So it will be about 588 MVA, around 600 MVA. So there will be 3 transformer interconnected with the proper vector group. So it is each transformer will be of size 200 MVA. It's a huge transformer. So we'll know briefly about all the large electrical machines used in PFBR. Then one special type of valve which is designed which is kept at the steam generator outlet to isolate it during maintenance. It's called frozen seal valve. So this is an application of buoyancy approximation of a Newtonian fluid for extended surface heat transfer, and I have specially designed the fin because it was one of the component design assignment given to me. So I have successfully designed the fin tube assembly. So this we will discuss slightly in details. Then we'll understand the 230 kV substation. It's a gas insulated system. This is a modular type of substation. It was supplied by Arriva France, and the connectivity is all the control and supervisory system is connected through the open gateway as per IEC 61850 protocol, I think. Then we'll know about the seawater system. It's a seawater intake system. There also that model study I was involved. It was carried out as per Hydraulic Institute standard 1.8, I think, NC. So there was a model study in Kirloskar Brothers and also in FCRI Palakkad. So I will share that some extent. Then one thing we started by the inspiration of always I used to tell my guru Dr. Perumal Chelapandi that here the thermal power which is generated in the reactor, it will be of 1260 megawatt, but finally we are able to extract the electricity only of 500 megawatt. So remaining around 750 megawatt of thermal energy we are simply dumping on sea by reducing the temperature. So if there is a technique, or we can evolve some technique so that we can extract that energy, so it will be a good thing. So we'll understand not much more in details. I started, but that project is in halt. Further I am not able to concentrate. So this is here the delta T will be around 7 degree, but large flow. Where the delta T high, small flow, there the heat extraction is very simple, but where the delta T is less but the huge flow, so there the normal water Rankine cycle will not applicable. We have to use some special type of design, so that we will discuss in brief. Okay. So then there will be conclusion and future scopes and the technical challenges in during the construction and design of first bit PFBR. All these things we will discuss and we will conclude the course. So today, just even though it's known to all, but as I told, for the new student, let me tell a few things about the Indian nuclear scenario and the three-stage nuclear program. So the natural uranium available in India is only around 1 to 2% of global reserve. So you know, natural uranium contains uranium 235 and 238. So where uranium 235 is very less, it is around 0.7%, and remaining is 99.3% will be in uranium 238. So here this uranium 235 only can go for spontaneous fission, through which the nuclear energy could be generated. But as we don't have the sufficient fuel, that natural uranium reserve in our country, so it's a great disadvantage. So seeing that, people will conclude, no, this program is not feasible or something like that, but it's not so. We have the thorium reserve. You see the thorium 232, 25% of the global reserve is available in India. It is in east coast of Odisha, Andhra Pradesh, Tamil Nadu, Kerala, in form of sand, in the sea coast sand, in form of monazite. Okay, if you see the salt, the wraith, sorry, the sand in Arabian Sea coast, and except that Kerala side, and the sands in our Tamil Nadu or Andhra Pradesh, you see this sand color will be slight brownish red. That is monazite, where around 7 to 10% in that sand, 7 to 10% thoriums are available in form of oxide or something like that. So this thorium 232, it's a fertile material. It cannot do spontaneous fission, but if it is converted to fissile material, then it could be used as it could be used to produce nuclear energy by fission. So this is the very 1 minute. Let me take 1 point. Okay. So this is the three-stage India nuclear program. So we are here at present. This is the breeder reactor, and I will very simply explain it and how it is interlinked and why it is. So if we see this first stage, if we see the first stage and second stage, and if you do a comparison of the contribution of nuclear energy in the total, in terms of total percentage of the energy production in the country, it will be very less, 2 to 3%, even though less than that. But it have a great vision and future, in my opinion. I joined in the department. I was a very simple, basically I am a telecommunication engineer. I working in software, cognizant, and I was my area of knowledge and my work was very limited. But I joined in the department with a great dream and vision that we will be able to utilize this thorium. So as I told, in the first stage of the nuclear program, Indian nuclear program, so this is a pressurized heavy water reactor where the natural uranium, and inside the natural uranium the fissile material uranium-235% is 0.7% only. That will go for the spontaneous fission. Means we will know about the fission in a elaborate manner by the application of nuclear reactor physics and nuclear physics, that if the critical mass is kept in critical volume and the neutron initiator is ignited, then the sustainable and if you are able to maintain the multiplication factor 1, then there is a sustainable chain reaction and it will continue to produce the thermal power. Okay, so this in pressurized heavy water reactor, the uranium-235, which is only at about 7%, this will produce depleted uranium, used uranium, as well as this plutonium-239. Okay, so this plutonium-239 we will be taking, it's a kind of, it's also a fissile material that we will use in the breeder reactor. Okay, so the byproduct of the pressurized heavy water reactor we will be using as the fuel in breeder reactor. Okay, so this plutonium-239, this will be the fuel. If this will be the fuel inside the reactor, and the outer blanket, if it is of thorium or depleted uranium, okay, uranium-238, then once the reactor the reaction started, then this, after this fission, whatever the fast neutron will produce, here in pressurized heavy water reactor we need to slow down the kinetic energy of fast neutron. So that's why we used moderator. That's why we used deuterium oxide as coolant, as well as to slow down the kinetic energy of fast neutron. But here no moderator. We will use the kinetic energy of fast neutron to convert the fissile material to fissile material. So assume if there is a blanket of thorium and the fast neutron produced by the spontaneous fission from plutonium, it is absorbed by thorium, and it will because this is thorium is 232, so one neutron, if it is absorbed, one unstable nucleus called protactinium of protactinium-233 will generate. Okay, which is radioactive, and it can further decay over a month period, and it will convert uranium-233, which is a fissile material. Okay, now if you see, if we can establish this second stage breeder reactor program in the country, then the byproduct getting from the first stage of Indian nuclear program, that will go for the spontaneous fission, and this will convert the thorium blanket or the depleted uranium-238 to uranium-230. If it is converted to this thorium is converted to thorium-232, if it is converted to 233, then we will, this byproduct uranium-233 will be using in the third stage, where this uranium-233 will be used as spontaneous fission, and the neutron generated from that will be again converting this thorium to uranium-233. That means the quantity of uranium-233 will be consuming in this thorium reactor. We will regenerate more quantity of uranium-233 which we consume in the fission. So now you can understand. Then we have the reserve of 25% of global reserve. So if we can reach here, then we will be generate 500 gigawatt of electricity for next 500 years. So we will be able to enlighten the life of the people around. I think around still today more than 200 millions of Indians are not connected to grid. We will be able to enlighten their life. We will be able to provide quality human life for the countrymen. Okay, so these two stage are the second and third stage of nuclear program. They are concerned with breeding. Why breeding? You see here this plutonium-239. So we will be using plutonium-239 and depleted uranium-238. So the first neutron, it is converting this uranium-238 to plutonium-239. So the quantity of plutonium-239 here we used after the breeding, means after the reaction completes, it is producing more plutonium-239, which is getting converted from uranium-238. So the what we used, we are as a byproduct, we are getting more than that. Quantity is increased. So that's why it's called breeder. In third stage also, we are using uranium-233. So this uranium-233 is, after fission, the first neutron is converting the thorium to again uranium-233. You see, this is called sustainable nuclear cycle. This was a dream of Dr. Bhabha. This was a dream. So definitely we will reach here, and once we reach here, it will be, in my opinion, it will be a great achievement. Okay, so this will be done. This is your pressurized heavy water reactor. This is your fast breeder reactor. It means sodium cooled fast breeder reactor, which we are working in Kalpakkam PFBR, and this is advanced heavy water reactor. Here we are not going for the light water reactor because of mainly 2-3 technological limitations. One is that the material and the component fabrication, so far India don't have the technology, as well as in light water reactor it needs the uranium enrichment. So 0.7% concentration is not sufficient for the light water reactor. It's need around 3 to 4% or 3 to 5% enrichment. We also have the limitation of technology to enrich the natural uranium. Okay, so due to those all disadvantage, we are going for this pressurized heavy reactor. I think in 4th August 1956, Apsara seen its criticality. Okay, so that entire design is by Indian nuclear scientist, and the fuel is from outside of the country, I think Europe or UK somewhere. Okay, so this was all about the 3-stage nuclear program and why we are going for breeder reactor. It is not, we cannot quantify or we cannot think today by seeing the energy contribution in percentage of Indian total energy, means how much energy is, how much percentage of energy is produced by nuclear power today. If you see that, it's very low, 2 to 3%, 4% maybe, not even more than 3%. You cannot compare that things today, because our target is to go somewhere else. Okay, so if we can prove this fast reactors, and through that if we can convert the thorium to uranium-233, then that's all. 500 gigawatt of electricity for around 500 years, no problem, we will do it. So that was the vision of Dr. Bhabha, is the father of Indian nuclear program. No power is costlier than no power. दुनिया में ऐसा कोई ऊर्जा है ही नहीं जो बिना ऊर्जा से महंगा हो सकता है. कुछ भी तरीके से आप by any means we produce power, ये बिना पावर से तो सस्ता है ही, किसी भी तरीके से करो. Okay, so this was all about today's discussion, and in the subsequent lecture series I will be discussing about the content which I told in the previous slides. So thank you so much. Thanks for your patience.